capacitors, voltage across the capacitor is going to control the input of a switch. That switch will become on or off according to that. This is my RD. So what is my voltage across C? VC will be how much? Okay, I'll draw the Thevenin's equivalent for C. Okay, these are very easy way to do the things. RTH I'm putting here. Here is my C. What is my VTH? This VTH. Though we are not going to use that in our discussion. What is VTH? Across the C. I open across the C here at this point. So voltage will be V divided by R plus RD into RD. Okay. So VTH will be V into RD divided by R plus RD. RD is the device. I'm not talking negative positive right now. RD is the device resistance RD. So that is becoming my VTH. And what is my RTH? RTH means voltage source will be short circuited, and this capacitor here, this terminal, I am looking from this. So there is no current flowing in this. With that assumption, we find the RTH. So R becomes parallel to RD. Will that be R parallel to RD? RTH will be how much? You already know. So that means your RD into R is my device resistance, R plus RD. And this becomes my C. Voltage and Thevenin's equivalent resistance I have computed across that. So VC will be how much? There will be VTH here. What will be this at this point? T by tau. Remember, their negative sign, e to the minus t by tau, it is charging according to that. Okay. Initially at t equal to 0, voltage across the capacitor is 0 because it appearing as a short circuit. Whatever comes here, it appears at this point. So voltage across the capacitor is 0. So that is satisfied by VTH into 1 minus e to the power. T equal to 0, this becomes your 1, 1 minus 1 becomes your 0. So your voltage across the capacitor will be rising like this. This is my VC and this is my T. And this one will be e to the power minus t by tau, and at this final will be your VTH. So VC will become VTH. It becomes a constant. Finally, it will appear like that. That's what we are getting. Okay. Now, suppose you have got a device, a circuit, whatever you say. There is one circuit, passive circuit. Also, we call it Bruton circuit. That's why I'm not calling a device here. It can be circuit also. Bruton. Bruton's negative. Resistance. Okay, so there is a circuit. It is not having any kind of your active device or something like that. No semiconductor, etc. It is on RLC circuit, gives me that kind of provision. Anyway, this device or this circuit is producing a negative resistance. So what happens? Suppose RD is negative, not equal to 0, less than 0. RD is negative. Negative resistance you are somehow we are getting. I'll show you how do you get that. If that comes, then what is my VC? That will be depending upon my tau. So tau will be what? RD is less than 0, then tau will be, you want tau to be greater than 1, isn't it? Or greater than 0 that way. You want tau to be greater than 0. RD is negative, so let me write here tau here. Tau equal to RD into R. RD is negative, so numerator becomes negative. Denominator R minus something is coming. RD is negative now, so R minus something. So till then denominator is positive. R minus this resistance is positive. I am going to get tau as positive. So my circuit will be in the stable state. I'm taking here this like that. RD is less than 0 and RD is smaller than R. So it is negative but smaller, sorry, RD is smaller than or no, RD should be greater than R, sorry. RD is greater than R, sorry. RD is smaller than 0. Okay. This negative RD, mod of RD I'm saying. Mod of RD is greater than R. So this is negative of the mod. The denominator also becomes negative. So negative and negative, this positive. So in this case, tau is positive. If RD is positive, it is always positive. Tau is always positive. RD is negative. In this condition, tau is positive. Okay. Second condition I'm putting, mod of this RD becomes smaller than R. Then what happens? Numerator here becomes negative because R is positive, RD is negative, that is negative. R minus some value is there, that is magnitude is smaller than R, so denominator is positive. Okay, so in this case, tau is negative. As a result, what happens here? This becomes, okay, 1 minus e to the power something like t by tau into, of course, either VTH is there. This quantity becomes very large if t is increasing, because e to the power, that is exponentially increasing, that will be larger than 1. At t equal to 0 itself, it is your 1. So it is becoming more and more negative. Okay, but magnitude is becoming unbounded now. If t becomes infinite, magnitude becomes minus infinite or something like that. So this will lead to unstable circuit. So your RD device resistance, it becomes negative And not only that, it becomes negative, its magnitude becomes larger than R. Only then it becomes unstable. So now we can get different stable states of the your switching system. So like your bistable, astable multivibrator, you have generated that with the help of the device itself. Any question here? Clearly I have explained that. That is the binding on the device, and how to bring that, now we'll see that. Is that okay? Fine. Simple thing. Now here, I am here now. Okay. I am repeating the same thing. When RD is negative, okay, and similarly, here negative, so you can say R minus RD, I can put it directly now, is also negative. Okay, so this implies circuit is stable. RD positive I am not considering because that you already have done quite enough. Circuit is stable. So we are applying the trigger makes R minus RD always negative. In whatever state it is there, that is stable state. If I apply a trigger there, it will go to some other location that will also give the same thing, R minus RD, because RD dash will be changing, R minus RD, R minus RD double dash. Both. Trigger makes it, once it is making RD equal to RD dash, it is stable. Now it remains there. When the second trigger is applied, it will meet the RD dash as RD double dash, that is also becoming negative. So that is also a stable state. So we can realize a circuit that will give me bistable. I cannot say multi-vibrator, you can say as a circuit. Multi-vibrator give when the NOT gates are connected back to back. Here the device dependent thing is there, so I call it bistable circuit. Okay. Here, second thing, I'm saying R minus RD is positive. RD is negative. RD is negative. I'm not writing mod again and again because you know that it's negative, so instead of R plus RD becomes R minus RD. Okay? Positive and R minus RD is positive. Okay? This will become unstable. So what happens? The device is biased such that R minus RD, initial state I'm putting as 0, is negative. Initially device is biased, so it becomes negative, and with trigger R minus RD, by putting as a trigger here, T is positive. Remember, RD is always negative. Okay? So R minus RD with trigger is positive. So this will, after the trigger is gone, so it had returned back there by charging of the capacitor. This will given a monostable circuit. Okay? Now there comes a stable circuit. I think I take a new page. Is it okay? You have understood now? What are the circuits are coming here?
Yes.
Okay, fine. Now coming to the other one. Coming to the A stable circuit. Here we are given RD is negative resistance. Device I'm using negative, and R minus RD, that is magnitude of RD is less than R, is positive. With both states of the circuit. States of output, not of the switch, of circuit output. That is VC, voltage across the capacitance. Okay? When R minus RD is positive, voltage across the capacitor, both states are, you can say, swing, you can say. Voltage swing of circuit output, that is a VC. So in both the swings, it remains R minus RD as positive. That kind of supply we have put over there. So what will happen? It will keep on changing from one state to another state. From one value to another value swing, it will keep on swinging. And that will give me a stable circuit. So device has made the circuit astable, bistable or monostable just by changing the DC biasing on that. Here that multi-vibrators circuit we are not using, device itself is doing the job in the case of your low pass RC circuit. Is it okay? So now we'll see some of the devices that are giving you this kind of characteristics. One such device is PN here. PN junction diode, okay? P type and N type, silicon or germanium both. Another diode is coming like this. Here is your N, here is your P. They have fused junction here. So here to here, okay, it becomes your N. From here to here, it is becoming your N. Sorry, made the mistake. Diodes are in the same condition, P and N. Here also I'm putting at P and N. So two diodes are now fused together. So it becomes your three junctions. Here junction is 1, 2 and 3 junctions. I can replace it by PN junction diode by another PN junction diode. These are the two terminals. Okay. This can also be represented as, here is your P, here is your N, here is your P, and here is your N. I make a cut like this. So what happens? This and this becomes your PNP transistor. And the upper one, this and this becomes your NPN transistor. So what we have done here is, I have taken a PNP transistor, this through the emitter it will enter there. Current location I'm putting like that, this is your base. So this is your PNP. Now base of this one, okay, base of this is your N, collector of this one is your N. Okay, so base of this is connected to the collector of the other one. So that one will be your collector. This will be your emitter going outside. And this collector is connected to this base. This collector P and P, this P is connected to the base P of the second transistor. So PNP and NPN transistors are made like that. I can call it as my B1, I can call it as my B2, or vice versa. You can call this as B2, call it as B1. Bases are there. This becomes your emitter through which current is entering. Here current is emerging. This is also emitter. So we call it as E2 and E1, or any name you can give. So this circuit, this device will be assembled like that. Can be realized like this. It can be realized like this for the analytical purpose. Okay. While discussing this device, we will not consider any biasing of the base of any of these transistors. Here inside, in between the two diodes, I am not putting any kind of your control circuit or so. When I put that control circuit, it will get a different name. When no control is there, I am saying no control. No control signal. No control signal. Okay. Only I am connecting this to the power supply. P will be given this supply. N should be given positive supply. I'm giving Let's put here like that. Supply I'm giving NPN, sorry, other way around. My positive supply to emitter current will enter and it will be emerging out from this emitter even like that. Okay, so this is positive, this is negative, I'm giving like this. No control signal is given in between. This is called PN diode. In some books, it's also given as pin diode. Okay, it has got 3 junctions in that. It has got 3 junctions. So how many layers are there? Semiconductor layers are how many? It is also known as 4-layer devices. So it can be made of silicon, germanium, whatever you are finding in the market. This can be realized in the lab also. We are connecting 2 diodes transistors like that. But anyway, that will not be your point of discussion here. So this is a 4-layer device, 3 junction device, PN device or pin device. All names are just supplementary to each other. They are adding that. They are complementary to or supplementary to each other. You can say like that. So that way. When this gate, this is your gate here. This is gate of what? It is closer to this P type. So I call it a P type gate, P gate. This one I can say N gate. If some biasing is given to any one of them, P gate or N gate, I think both of them you are not giving the biasing. You will know the region if you look inside the, semiconductor characteristic of that. Normally we bias at any one of the gates. So N gate and P gate you are using. If you are biasing this gate also, okay, then it will give rise to the device, we call it silicon controlled rectifier. Silicon controlled rectifier. Another device comes in the similar category is thyristor. In both the cases, gate needs to be biased. So in silicon control rectifier, the layers are of silicon. Silicon is used in the layers. All the 4 layers, silicon is used. P type, N type, you are making for silicon only. So at that time we call it silicon controlled rectifier. In power electronics, silicon controlled rectifier is used. Another case is thyristor. This is made of germanium. Mix the layers. So you are using silicon diode, connecting them in a series. It will be silicon control rectifier kind of architecture, germanium diodes will give you known as thyristor. Okay, their operating range will differ, and that's why in different application, different one is used for cost benefit as well as for the operating range. The trade-off between the two is considered. So SCR and thyristor are coming according to that. Most of the cases in power electronics, people talk of SCR. Thyristor is not used that frequently nowadays. So SCR is the one that is used for, because silicon has got some advantage over germanium, so that is there. So this is your pin diode in which no biasing at the gate is considered. If I bias at the gate, it will become silicon control rectifier, or you can say thyristor if the layers are not made of layers are not made of silicon material. Is it okay? Is the introduction complete? These are the three devices which are using in your negative resistance. Another one is which you already read in your maybe your second year, first semester, or maybe your first year itself, some teacher had taught you. That is known as tunnel diode. Tunnel diode is a two-layer single junction diode, but it is giving some property of negative resistance. Okay, so you can use that also. Some negative resistance comes in, also gives negative resistance. If properly biased. Here it has a very properly biased. And this bias, this operating range is very small, so it's properly biased. The difference is tunnel diode is voltage controlled. I'll change the voltage in steps. I'll observe the current. I'll control the current. So voltage controlled. It is voltage controlled. Okay, so here the independent variable will be the applied voltage across the diode. So diode voltage I'm changing, and accordingly current is changing, which gives me negative resistance region. Okay, so it is called voltage control. Whereas in case of pin diode, SCR and thyristor, all these three are current control. I'm writing here current control. That means I'm changing the current value entering the device, okay, in regular steps for making observation table or so. So independent variable is a control entering the device, and we are observing the voltage drop across the device or some portion of the device. Okay, so we call that current controlled devices. So voltage control device, current control device. Now that is the difference. I will talk of tunnel diode also. How does it come? But most of the cases we use pin diode, SCR and thyristor. And SCR alone is sufficient to give the property of pin diode as well as thyristor. So that's why in the market, most of the time you'll find availability of silicon control rectifier, not others. Any question here? I welcome. No question? So all I've understood now. It's okay. So let me start with pin diode. That is the basic building block of this negative resistance. This is pin diode. Here, this is my voltage. I'm giving the voltage here like this. Okay. So now this voltage V or certain V, I'll observe what is the current flowing through it. And I plot it. This is my V, this is my I. Remember, I will be changing I in step because this is current control device. But plot I am showing with respect to my voltage. In fact, if you like, you can plot like this. This is my I, this is my V. So when I am changing my I, that means there is a resistance here. I am putting a resistance here. This I am putting like this, potentiometer kind of thing. So this resistance I am changing for same voltage, or you can say I am changing the voltage that is coming corresponding to a particular current. Okay, so initially the voltage will be very small because nothing will be flowing through this
Yes, sir. Good morning. Good morning. बैठिए ये सब बहुत डॉक्यूमेंट हो गए इनको फाइलिंग कर रहा हूँ
नहीं कौन बात कर रहे हैं कोई बात कर रहे हैं क्या इसका खुला हुआ है
सॉरी
माइक्रोफोन चेंज कर दीजिए आप ओके वी और वी when I am increasing voltage across the diode is not appearing because no current is flowing through the NP. This becomes your reverse bias. This third, the middle junction becomes reverse bias. Current is entering through that. So it's a very small current is flowing. And I think you already understand. When this becomes a breakdown condition of this NP, at that time, what will happen? Voltage across this will appear. Okay, there will be, sorry, I made a mistake here once again. Sorry. This plot, I'm confusing the two plots. Here is my I, here is my V. So when I'm changing my I, my voltage is constant. Constant is slightly increasing with some linearity or so. It is increasing like that. Very slowly it is increasing. When the breakdown occurs here, okay, this voltage will drop. Current will be increasing, but voltage will be dropping. Now it will come to this point, some point where voltage will be low, current will be high. After that, what happens? This will reach some kind of your saturation stage. Before going to the damage, at that stage, it will become some kind of current, homogeneous, P to N. This becomes a forward bias diode with some kind of short circuit appearing over here. So if I'm increasing the current beyond that, the PN junction, this forward bias resistance will work as a diode and it will come like this. So I is controlling this V. No other bias I have given. In fact, for biasing the circuit, I'll be using this. Here what happens? Initially, when I'm changing my current, I'm changing voltage, okay? This is my current is increasing up to this point, then current becomes very high, and after that it goes like that. it become saturated also to some time, because PN junction saturation current in the forward direction, that will be there. So this is S curve, V coming like this is the S curve. What happens here? My voltage was increasing up to this point, current was increasing. Now at this point, current has increased. In this year, current is increasing, but voltage is decreasing. This we cannot observe, cannot be experimentally observed. This region, suddenly it comes to this point. Okay, after that it starts like a PN junction diode, linearly increasing, and it becomes saturation, so it will be like this. PN junction diode coming like that. We are interested in this region. It is same thing, current control, but I plot it in the voltage control thing. Okay. So we have to bias. Suppose I want to bias in bistable region. I have to choose this value of current. Okay. And I have to choose somewhere this value of current. Or you can say, I can choose this value of the supply voltage, high, this I can choose as low. This is my I low, and this is my I high. So either it is selected according to the currents, step jumps are so, but in terms of voltage also you can see this is V low, this is V high. So what I do, initially I will bias it somewhere here. This is my bias. When no trigger is applied, it is biased here. If I biased here, I may remain here, I may remain here, I don't know. Doesn't matter. Even if I am here, I will have to apply a trigger for that. If I am here, if I apply a trigger, that trigger will bring it here, this position, and the level will be high at this point. Now trigger is gone, it will start decreasing. It will come up to this point. Below that it cannot go because this curve is not observed. So it is coming on this line, somewhere up to this point it is coming. Okay. So if it is somewhere, if it is biased at this operating point, first trigger should make it this one and it goes to that state. Suppose it is biased at this point, operating point, because of the initial condition of the noise and electrical noise and other things such as fluctuations, I am here. Then when I apply the trigger, it will bring that voltage down to this voltage, to this point. So this curve is bypassed. I have come to this particular voltage. This current is flowing. It is also stable now. So from high state, it has come to the low state. Okay. It is not returning back to this operating point position. Remember, here it remains here after the circuit has been triggered. Then a positive trigger at this point will bring it here. It will go to the stable state. Even trigger is gone, it will be coming, or you can say if trigger is gone here, it will return back to this state. Here also trigger is gone, returns back to this state. I'm drawing it here once again. It's gone. I have biased it at this point. This is your VB bias. Device biasing I have done at this point. If it is this, I apply a trigger, it will go to this point. Trigger makes it this point. VB rather, VB plus V trigger. I brought it, it has come to this point. Now trigger is gone. So it will start reducing to VB again. So it has come up to this point. Okay, it has come up to this point. But it is remaining in that state itself. Now another trigger makes it negative. Second direction. So here this voltage, apply the trigger again, it will come to this point. So this is your this point. So it was this point, now it has come to this point. And now trigger is gone again, so it will start moving to this bias. This is also a VV bias. This is also VV bias. So here it was coming to this point, here it is coming to this point. Okay, so here it is your VB minus VT, brings it here, it comes up to this point. After certain time period, you are applying VV plus VT, it comes to this point, and that's what bistable is operating. You can make monostable, astable also similar way. That I will be talking tomorrow. I stop here. Any quick question? I welcome.
Sir, results of quiz 3.
Result of quiz 3, I think I asked so many, you are coming late then. I asked your question, sir, have you got it, your answers mailed by the teacher to you or not? No, everybody accepted it as if it has been mailed to them. Answers are mailed or not? Answers are mailed to you or not? So if there is doubt, I can discuss that. Otherwise, I mean, the total marks the teacher will send to you. Total marks, I don't know. Normally they send the total marks also. But if the answers are mailed to you, you just tally. If anything is wrong, you can ask that question. That my sir, my answer is not like that. Why you have chosen like that? Can it be some other answer also as well? That way you can discuss. I started my talk like that. You come in the beginning first, because normally the next class I do this. Anyway, I will be meeting you tomorrow. Tomorrow you can bring those doubts. If I will upload my answer in the file itself, the teachers have not mailed to you. I don't know if they have not mailed, then I will upload my file in general section as a EC353 quiz 3 solutions, I can say. Okay? You tally that. Marks will be mailed to you by the teacher. I don't know when they will send the marks. It's up to them, but normally they send, or usually they are sending quickly, immediately. Second years, usually third year, is taking time. I don't know what for. Okay, then I will upload that today itself. Just now I'm going to upload that solutions of quiz number 3. You can see the file. Okay, and you can evaluate your score. If score is not tallying to that, you can consult the corresponding teacher or to ASU. Okay, good day. See you again.
Thank you, sir.
Okay. You can see the solution. Okay, I have upload that. I don't know if last 2 questions were, some questions were modified in the end. 1 or 2 questions were modified. So I will be uploading the original one because that is not there with me. So original one I'm uploading, you can tally that like that. If it is not there in the question, 1 of them or 2 of them, I think the respective teacher will be sending that. Look, I have not seen those questions. Couple of questions or so. Okay, let me upload that. Thank you very much for patiently hearing. Good day.